till the last time we had, I think it's been quite a long time, somewhere around mid-April is when we last met. And till then, we had discussed things about structural arrangement, components of bridges, and loading, and up to the definition of the characteristic loading. Now we will move on towards the general analysis concept. And even in the analysis concept, we will start with the understanding of uh, modeling any bridge system. So we'll start with that. Okay. So let me start by sharing my screen. You're able to see my screen? Okay, right. So when we talk about modeling any bridge system, before we start, well, let's do a quick recap of the uh, various things that we need to do in the modeling. We basically need to model the flexibility of the bridge correctly. And what does the bridge consist of? Let's recap: soil, foundation, substructure, bearing, and the superstructure, the whole lot of it. Okay. So if we have a good estimation of stiffness, then we will have a improved demand estimate, whether it is in the form of a force resultant or deformation. So to recap, what is our understanding of force resultant? What are force resultants? Yeah. What are force resultants? When we talk about analysis, we have been doing analysis for some time. We do modeling. So what do you call, what are force resultants? Nobody? That's sad. Okay, Milind, what is force? What are force resultants in any analysis? Hello?
Yes, sir.
What are force resultants in any analysis? So we have a problem with understanding of our terminologies. So
Force for
we that is so all these are classified as force resultants. Bending moment, shears, torsions, axial force, compressive, all of them are collectively called as force resultants. You might have seen this force resultant terms elsewhere. If you're in a code, this force resultant term is very clearly and explicitly used. Do you recall which code? 112 doesn't use it so explicitly as another code, which we refer to. No, 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 no. 114 in one form, yes, but 114 derives itself from one another basic IS code. Ah, 1893. So where have you seen the word force resultants used there? Where have you seen the use of the word force resultants there? Huh? Okay, you would have seen them in You'd have seen them in come out of just 1 second. You'd have seen them in the combination rule. Do you recall the combination rule? You all know that it is the combination rule related to multi-directional earthquake. Do you remember that? Yes. So when you have that, the code says you have to combine individual stress resultants, and that's where the combination rule is given. And quite often we misread that code. It has if it has changed, that is a different matter. But earlier, the combination of 30%, 40% are the uh, three components. They're all the addition of the individual stress resultants. So when we talk about stress resultant, then it should be a same type of force. It is not a combination of mx with my. But anyway, that's a different matter altogether. So stress resultants, if you want to get a correct estimate, then you need to have your flexibility of the whole system estimated correctly. And if the flexibility has to be estimated correctly, your modeling has to be done correctly. So therefore, we need to understand the different aspects of modeling correctly. So we look at the modeling from the point of view of geometry and discretization as the first step. So anyway, you have to make a correct considered choice whether we have a slab type, girder and slab type, box girder, truss, arch, integral, whatever be the big structure. The structural system itself has to be made correctly. After you have made the correct choice for this, each one of them will have a slightly different requirement for discretization. But in general, you need to follow the fact that you need to model all the components of the bridges inside your uh, analysis modeling. Every component. What are the various components? You have soil, you have foundation, you have substructure, bearings, and superstructure. Say if this is a view in the longitudinal transverse direction, and in the longitudinal and in the cross-sectional view, whether you see superstructure may also have an alternate arrangement, the type of substructure in the form of either a portal or a single cantilever pier. Whatever it be, you need to model all of it correctly. Now, when we do this model, we are faced quite often with questions. What are the questions? Now, typically our bridge piers are prismatic members, correct? So, in prismatic members, quite often we follow which discretization do you follow often? The left hand side or the right hand side? Which discretization do you follow? Left hand side. Why? So because it is prismatic, you say you follow the left hand side. Is that correct? So if we follow the right hand side, is it wrong? It is not wrong. Now we will understand what happens or does not happen with respect to discretization. So the left hand side is called the coarse discretization. And the right hand side, what will this give you? It will give you, where will it, this kind of analysis will give you stress resultants and deformations where? At the ends of the member where you have chosen to have the discretization. And when you have a finer discretization, if you want the forces, I should use the word forces, when we want to have the stress resultants and deformations at other points, we make this. But when you do this discretization, what is the definition of a member in any model? What is a member? the element that connects two nodes. So in the case of this, the element is member is from here to here. The same member, when you do finer discretization, will be broken into sub members. So you will become 1, 2, 3, 4, 5, 6, 7 members. From one member, it becomes 7 members. Now, when you do this discretization, in the first case, basically what you are saying is that I am not interested in the effect of shear deformation. We'll come back to understanding the flexural deformation and shear deformation in a short while. But basically, you're saying when you do coarse discretization, you're saying that I'm interested only in the flexural deformations. I'm not interested in shear deformations. Now, we'll understand what are flexural deformations and what are shear deformations. Before we go to do that, then in the case of a prismatic member, this is a choice whether I do coarse discretization or fine discretization. But if we have a non-prismatic member, like for example, we have a pier which is small at the base and large at the top, then this is not a choice. This becomes a compulsion, because if we want to get the correct stiffness, we have to discretize it to get the geometry of the pier more accurately modeled. You understand the point now? In the case of a non-prismatic members, it is not a choice. It is a must. It's a compulsion. But in the case of a prismatic member, it's a choice. Now, in both these cases, what it means is that the shear deformation effect will automatically get incorporated when you do the finer discretization. Now, when it comes to non-prismatic members, you have a further choice. If I have a pier like that, I can take the inner size for the model, or I can say take the outer size as the model. Which of them is correct? Is the average also correct? Average is also what? So average is a third choice, but it is essentially still a choice. So the question comes between the left side model, which is the inner dimension model, and the right side model, which is the outer side model. What are the problems? If there is a problem, is there a problem? One. And if there is a problem, what kind of problem is it? To understand that, you have to go back to the first thing we said. What is the aim of all modeling? The aim of all modeling is to get the best estimate of the stiffness. Correct? So now there comes the question between the left hand side, which is the inner dimension model, and on the right hand side, which is the outer dimension model, which is correct? Nobody wants to take a chance. Why? Is it true? Is it true? Is it true in all cases? Others don't have an opinion? And maybe I should ask individually. So, Shreya, you have an opinion? Which is correct? Which is better?
I feel like both
No
have
feel.
some
No
problems.
feel. No fence. You take a choice.
Then probably the outer size.
Outer size. Why?
The inner size will also not be accurate. The
We we
the
have
the
we have agreed that both of them are approximations. The question that is
yes.
asked is which approximation is better and why. It's not enough to pick a choice, but you should also know why. Yes, Shojit, any opinion?
So for the inner size, the stiffness will be lower, so it might result in more conservative design.
What is design? What is design? Okay, so then the question is only some of the thoughts that we exchanged in the previous classes are. So, Maudharni, your view?
Sir, both is having their
Both of them are approximate.
is
The question is which is better.
sir, when coming to the inner size, the section size is very smaller. In capacity point of view,
What
uh,
capacity? We are now talking only in analysis. We have not come to design yet. You're only talking about analysis and therefore modeling. We are going to estimate the forces. So from that point of view, which is better?
yes, sir, the outer size too is having a more stiffness and it will attract more force. So
So higher stress resultant. Therefore,
yes, sir.
preferable.
Yes, sir.
What about Milind?
Sir, outer size.
Outer size. So you're all consistently with the outer size. Okay. Now let us say I have another way of, I don't use the self-weight option of an analysis software. I put the exact self-weight as I calculate. That can be overcome. You agree? Self-weight is, it's a problem only if you use the internal self-weight calculating mechanism. Okay. Now, if I were to say the choice of the model depends upon what is in your judgment the governing stress resultant. If I were to say that, and the governing load condition, if I were to say that, do you recall this picture? Do you recall this? Or you have not seen this at all? Yes, please. Do you recall this? Why? See, if you take a look at the this diagram, we are talking about the amplitude of the forces and the other axis, the natural period. The other one is the natural period for wind and earthquake. So, if you take the outer dimension, what are you doing? You are, when you take the outer dimension, you are underestimating the natural period. And when you underestimate the natural period, what is the consequence? When you underestimate, yes. and lower estimation of deformation. So when you take the outer dimension, you are underestimating deformation, but you are conservative with respect to evaluation of the earthquake forces. But if you take the minimum sizes, what are you doing? You are overestimating the deformation. You are possibly overestimating the wind effect and the wind dynamic effect. So, which is the correct modeling? So, which is the correct modeling?
Sir, outer size for shorter.
But you
Shorter
are
structure.
so are you going to do 2-2 analysis now onwards? 2-2 model?
Not actually.
Then what will you do? So what it means is, so what it comes down to mean is, you must develop over a period of time the judgment of which phenomena is likely to be more critical, earthquake phenomena or wind induced phenomena. If it is wind induced phenomena, then if it is in your judgment going to be the more critical phenomena, then you should use which geometric discretization? Inner or outer? And if it is earthquake based phenomena which is going to be critical, which geometric discretization? Exactly. So now you understand modeling is not that straightforward. What it also means is you must have a good idea about what kind of structure you are planning and what kind of structure you are going to design, which area you are designing, what are likely to be the most critical design conditions. And accordingly, you should choose your geometric discretization. Okay, so don't assume that, because the reason why I can understand where your reactions are coming from. You haven't done slender tall bridges, you have not done ceilings, you have not done say bridges with very tall piers, correct? Yes or no? And therefore you are conditioned to say that all bridges are alike. That is what is the myth I want to bust. You have to be aware of what are the various things that are possible and then take a call. Okay, now let's come back to next step. After you've seen the geometric variation, how to handle it and what are the complications related to that. Now coming back to the modeling, we have a simple portal substructure where we have the left hand side discretization, which is node to the center of the member, and a right hand side discretization, which is modeling the clear length of the member. Now, which model is correct? Why? So therefore,
The length of the member.
yeah, go ahead, one by one. No, go ahead. So one is the exact length of the member is model. So why is the left hand? But how often do you do the right hand model? Why? Huh? Okay. Why is it really giving you the more stress resultant? No. Now we come back to the same old question. Let us now go back to your traditional significantly largest number of structures that you have done. So when you do the left hand model, what are you doing with the flexibilities and rigidities? Left hand model, you say that's the one you should do more, and you said you prefer to do it because you get higher stress resultant. Why do you think you get the higher stress resultant? So, but you are always designing at the face of the joint. So you really don't design at the joint force itself, or do you? No. All shear and flexure both. So are they more between the left and the right? So are we doing right by doing the left model versus the right model? So coming back to the same old question, which always haunts us, which is the correct model? The left side model or the right hand side model? Why is it so difficult? You should not forget your logic. You should go back to the same old logic, which is the question is, let's go back to right or wrong first. In the case of the right side model, we have used a rigid or semi-rigid link as an offset from the center line of center point of the joint to the face of the so-called member. Is that modeling correct or not correct? If so, why? Huh? So why is it correct? Then why don't we model them always like that? Why do we do the left side model if we know that is left side model is not correct? So why don't we always do the right side model? You only told me most of the time we do the left side model. If the right side model is the correct one, then what exactly are we doing on the left? There's another problem which you are doing by using the left-hand side model. As far as the column stiffness is concerned, or the pier stiffness is concerned, are you overestimating the stiffness or underestimating the stiffness? No, on the left-hand side. So you have got duplicate stiffness. That is one part is correct. But what about EI by L for the column member? So which is correct? Right? So therefore, the problem with the left-hand side model is there is a duplication of the member properties in this section, where there is no duplication here at all. Here, there's because of the increase in L, the so-called aspect ratio, L by D ratio, you are reducing the stiffness of the column member, whereas you are not doing it here. So therefore, the finite size joint modeling is the correct way to do it, subject to the particular type of structure that you're doing. It is not necessarily significant in all the cases, but its significance is recognized in certain very explicit condition in our code IRC 112 or the Eurocode. Centerline model is simpler. Centerline model is simpler, and that gives you reasonably accurate results under certain circumstances, especially when the bending behavior is significant. Okay, we'll come back to that next step. All right. So we come back to discretization again, single member discretization for column pier and wall pier. Column pier is a slender member and a wall pier is a squat or a short member or a short column, if you want to use the slender column, and short column is something that is easier for you to understand, a slender member and a squat member. What is the difference between them in terms of the stiffness? What's the difference between them? Is there any difference in their stiffnesses? Yes or no? So what's the difference? It is more because of the I value for it. Now, coming back to the question, suppose I do a finer discretization of the so-called slender member. Then the member becomes by definition that between the nodes, correct? Then this member, is it slender or squat? So therefore, when you do a finer discretization, you are converting even the slender member into a squat member. Now, there are some fundamental behavioral differences between a slender member and a squat member. And to understand that, we should understand the concept of deformation. Suppose there is for ease of understanding, we will take a simple cantilever member and we apply a lateral load. So there are two types of deformations possible. One is a flexural deformation and one is a shear deformation. What is the difference? What's the difference between a flexural deformation and shear deformation? No difference? What's the difference? So let's talk it. We are talking about deformation. So let's stick to the deformation. That means what? The left side member length increases and the right hand length decreases. Just hold on 1 second. I need to take a call. In the case of a flexural deformation, the left side fiber and the right side fiber, they change in length, and it is represented by a continuous change in the tangent to the curve with respect to the vertical height, which we call as rotation. There is a rotation here, but in the case of flexural deformation, the rotation is a continuous rotation. But in the case of shear deformation, the left hand fiber and the right hand fiber do not change in length. It is just that this rectangle, the blue rectangle, becomes a parallelogram, whereas the blue rectangle becomes somewhat like a trapezium in the case of flexural deformation. This is the basic characteristics of deformation, right? And therefore, for a simple cantilever, if we have to understand the stiffness, what's the stiffness for a simple cantilever? Stiffness. No. Okay, I'll grant you that way. It is 3 EI by L. I said simple cantilever, but in you talked for general member in flexion, EI by L. What is the shear stiffness of a member? What's the shear stiffness of this member? And from the EI by L, you recall the basic, huh? No L, GA. Okay, only GA, right? These are the basic equations. If you recall our traditional structural analysis equations for the flexure, EI dVb by dB square by dx square is equal to minus n z2 plus qix, right? And for shear deformation, it will be simply Ga dvs by dx is equal to shear, right? Now comes a question: what is the significance of shear deformation? Okay, to understand the significance of shear deformation, do you recall the conventional flexural 4x4 stiffness matrix? Can anybody tell the terms of the traditional flexural stiffness matrix? No. The traditional 4x4 stiffness matrix for flexural effects. Is bad. How can you forget it? Okay. We will go through it in that case. I mean, it's so if you take a look at it, I think if you ignore this By term, if you take By equal to 0, if you take By equal to 0, 4 EI by L, 2 EI by L, okay, 2 EI by L, 4 EI by L. Now is it familiar? Yes or no? Hello?
Yes, sir.
Now the question is, when you have shear deformation present, which is present in almost all structure, this 4x4 stiffness matrix gets modified by the term 4 plus By, Ey by 1 plus By, 2 minus By by 1 plus By, 2 minus By by 1 plus By, where beta y is 12 Ei over Gasy L square. And if you make it simpler, 12 Ei by L cube you put, and at the denominator you introduce modified, that is basically divided multiplied by L, you will get Gasy by L. So under what circumstances will this stiffness equation reduce your pure conventional flexural stiffness matrix? Under what circumstances? Never? When? If the length is very large, I will say that it will go to beta will tend to go to a 0. So therefore, beta will get to go to 0 when length is very large. But if the length is very small, remember that E and G are related. I and A shear Y is also related. So the only parameters you have to play around is L. So if you want, when you want the beta to tend to 0, you need GAS by L tending to a large value. And if that has to go to a large value, L has to become small. When L becomes small, GASY by L becomes larger value, and then it will tend towards 0. I'm sorry, the other way around. This will become a larger value. When L becomes smaller and smaller, GASY by L will become large value. And therefore, this equation, when this will tend towards 0, and you will have a more conventional equation. But when you want the member to be more shear deformation to be small, to understand the impact of it, imagine that you have two columns, 1 meter by 1 meter, 6 meter long column, and 1 meter by 6 meter, 6 meter column. So when you calculate the beta value, you will realize that beta y, the ratio beta y is nothing but the flexural translational stiffness to shear translational stiffness. What it means is, when beta tends towards 0, flexural translational stiffness governs the deformation, and when beta becomes a large value, shear translational stiffness governs the displacement value. Ultimately, this is nothing but the force deformation relationship. Force into stiffness is equal to deformation, and therefore, for a particular set of force results, the deformation will become governed by either the flexural translation or shear. But most often than not, they both play a role. Now, when you see this relationship, it should tell you one thing. In all your modeling, what have you been doing about the shear deformation? What have you been doing about the shear deformation? the question now is, are you using them or you are neglecting them? Or you have no idea what we are doing? That's also possible. The third option. So now I want you all to go back. Whatever models you have been doing, whether you have been using the shear modulus and the shear area definitions in your model or not. If you are not doing it, from now onwards, all your models should have shear area definition and shear modulus definition. It should not be arbitrarily given. See, there is one way to do is you give a very large shear modulus or you give a very large shear area. So then what happens is beta tends to go towards 0. Then you are artificially saying that all my deformation should be flexural deformation. So what will happen is you will be actually, wherever shear deformation is to be governing, you will find that also you are getting ignored by the way you have modeled. Please remember, what we are going through today is understanding the impact of modeling on your analysis. And therefore, it is important for you now onward to go and check in every model, make sure that the shear modulus and the shear area is defined correctly, and then only you do the analysis. Okay, we'll come back to the impact. Now, if you take a look at it, if you take a normal column 1 meter by 1 meter by 6, you will notice that the ratio of the beta y, which is the ratio of the flexural deformation to shear deformation, is very small. Okay, and in the case of this, the ratio is very large, which means what? Shear deformations are significant in this, and if you try to treat this as a flexural member, you would be making a gross underestimation of certain effects. Okay, and if you take it, look at it in the stiffness matrix itself, if you went for this kind of a column and let us say you accounted for shear modulus, you will notice that this comes to almost 4, 1.9, 3.96, 1.9. That means this is close to a flexural deformation controlled behavior. But if you do one, my suggestion to you is, quite often you are using 1 meter by 4 meter, 8 meter tall column, and you are ignoring this beta altogether by not declaring the shear modulus and not declaring the shear area correctly. But if you declare it correctly, you realize your stiffness matrices change drastically. This 3.96, which is close to 4, becomes 2.22, and this 1.99 becomes 0.22. Which means what? Basically, what you're telling is that the ratio is altering, the deformation behavior will change, and therefore every other aspect with regard to stiffness, etc., will change if you ignore the shear deformation effect in your modeling. And this is particularly true for all bridge pier. Now I want you to take an oath that all your modeling you will account for the shear deformations correctly, irrespective of the geometry. You will not use the option of ignoring the shear deformation. It will take some time for you to get used to the slightly different results that you're likely to get, but better to get used to it than do it wrongly. Okay. Now, in further discretization, you subdivide the primary structure into members or elements, and you choose nodes. And then, as we have seen earlier, you use the rigid offsets method. Then you should normally not have closed loops. Normally not have closed loop. But for example, if you model the box structure with this, there will be closed loops. Okay. So that is one thing that is not, but generally when you come to close to foundation, the closed loop can be open. Otherwise, you should have open loops in all the places so that you have a proper discretization. Then to understand the discretization, we always use the Cartesian coordinate system XYZ, and for these XYZ, then we have the degrees of freedom associated with these Cartesian coordinates. So we have displacements and rotational degrees of freedom. And these are in general. In general, there are 3 translational degrees of freedom and 3 rotational degrees of freedom at every node. At every node, which is that is to say that. But however, depending upon the type of structure and therefore the discretization, at each node, degrees of freedom for a member will depend upon the nature of the member. So you will see a linear bar will have 1 degree, which is essentially the axial deformation and axial rotation. There's no rotation at all. There's only an axial deformation, so 1 degree. There's a planar truss member. It will have 2 degrees of freedom. It's a space truss member. It will be 3 displacements only, no rotation, only displacement in these. Then you have a planar frame, space frame, and grid or a special space frame member. So where does the beam fit into it? Where does the beam fit? Beam. No, 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 no. Where we, so now I want you all to get used to the fact that don't ever refer to any element as a beam element. Start referring to them as a frame member. Don't use the word beam member. Frame member and truss member. These are the only 2 members, 2 types of member terms that you should start using, so that once you use these terminology consistently, then you'll automatically know what type of degrees of freedom and what type of force resultants you are talking about. Okay, so don't get out of that mode of discussing in terms of beams. Talk in terms of frame members. All right. So let's go back to at the member coordinate level. At the member coordinate level, we have the member stiffness matrix. Displacement vector is equal to force vector. This is the classical equation. And if you put it with the element, you can write it for each element. Now this is the classical one, in which what is the problem with this equation? We have ignored all shear deformation. Correct?
Yes, sir.
So this is at the member level, but when we go to the local coordinate system, that 4x4 becomes an 8x8 matrix, which is considering the 2 ends of it together. So you have all this the axial deformations also joining the thing. So it will become 6x6 matrix, as we call it, not 8x8, because the axial deformation is also added into it for a framed member. All right. The question now is, in this stiffness matrix, if we bring in the ratio of the shear deformation to flexural deformation, then at member level the stiffness matrix gets modified to 3x3 like that. We have added the axial component also, and at the local coordinate level we end up getting a stiffness matrix of this nature. Now comes the interesting part. Let us say that our beta tends to 0. When will beta tends to 0? When we essentially are saying that our shear stiffness is extremely large. Okay, when beta tends to 0, we have basically the flexural governing all of the criteria, shear not governing, and we go back to our classical 6x6 matrix, which we know so very well. But on the other hand, let us say the other way around, where the shear deformation starts governing, that is beta tends towards infinity, then this stiffness matrix gets to this shape. Now there is a problem with this stiffness matrix. What is the problem with this? That is not the question. The answer is self-evident in front of you. The answer is evidently in front of you. There's a term for this kind of matrix because of a particular situation that is present there. The matrix is called an ill-conditioned matrix. Why? Why is it an ill-conditioned matrix? And what does an ill-conditioned matrix indicate? Not clear? What do you see here? This and this. What are they? Zero. And they are sitting on what line? On the diagonal, if you have a zero, it's called an inconditional matrix. And what will it hint at? It will hint at instability unless you have something else connected which takes care of stiffness here. You will not be able to solve the matrix. Okay. So therefore, what does it mean that you don't go and discretize it too finely? A linear member by introducing so many nodes that you will end up having a very, very high shear deformation based deformation control, and therefore you will lead to ill-conditioning matrix. Your results will be quite unreliable. So your discretization must also have a certain reasonable limit. Okay, to understand that, if you take the load deformation relationship and we take the effect of L by D. Okay, so we know the beta y, the definition, we go back to the same 12 EI by this. Now, if we take a look at that and you add up the relationship between E and G, when you add this in with the Poisson's ratio, you end up getting that beta y can be reduced to a parameter 2 into 1 plus nu by L by D square. Right? So what does it mean? That when your L by D is large, your beta is very small. Your L by D is large, the beta is very small, and therefore your matrix will never be ill-conditioned. But as your L by D becomes smaller and smaller, your beta y goes on increasing, and your matrix tends to go towards the ill-conditioning. It will never get ill-conditioning fully, because you can never create an infinite stiffness, but it will tend to go towards ill conditioning, which means what? Which means basically you're telling by modeling itself, I'm making sure that the flexural effect is negligible and everything is going towards shear deformation. That is why your modeling and discretization are important in how you do it. There must be a reasonableness to it. So you must have a good idea in what range should you treat your L by D for when you are discretizing. This whole thing was only to explain to you the importance and effectiveness of the L by D in determining the beta y value. And in the previous thing, we have said that if the beta y becomes very large, the matrix tends towards ill conditioning. And once it goes towards ill conditioning, your results are unreliable. Okay. So you can see that this can be towards infinity or towards 0, and you should have a good choice as to where you want to fit it in. Okay. So to understand it in some more term, let us say that you have a rotationally restrained cantilever. What does rotationally restrained cantilever mean? That there is a rotation is made 0 at the top of the cantilever and the bottom is fixed itself. Can you give one example of where this situation can arise? Where can we have a rotationally restrained cantilever? Imagine a very stiff superstructure connected to a very flexible substructure. Then it's possible, though you will never get a fully one, but that is the situation where you could have the substructure being rotationally restrained, and for which when you have the normal flexural system rotationally stiff, when you ignore the shear deformation, your normal flexural stiffness 12 EI by L cube, but the same thing with shear deformation becomes 12 by 1 plus beta EI by L cubed. So that's how the lateral stiffness changes if you have shear stiffness or if you ignore the shear stiffness. Now, similarly, if you have a rotationally free cantilever, 3 EI by L cubed is the very well-known conventional lateral stiffness, but it becomes 12 by 4 plus beta EI, and when the beta becomes 0, it becomes a conventional 3 EI by L cube. Okay. Now, if you take a look at a rotationally fixed sphere and you take the ratio of the flexural deformation to the total deformation, shear plus flexure, which will then get reduced to 1 by 1 plus beta, or ratio of shear deformation to shear plus flexural deformation, which will be reducing to beta by 1 plus beta. So if you take a look at it for various L by D ratios, you will note that when the L by D ratio is 1 and the beta y is 2.5, about 30% of the deformation is due to flexure and 70% is due to shear. But you just have to change the L by D ratio to 2 and it dramatically changes from 30%, it becomes 60%, and that becomes half. And if you keep going that way, you will notice that L by D ratio, if you are sure that it is a flexural member, it is a reasonably flexural member, then you should not discretize in such a fashion that the individual L by D ratio, I would advise you against going anything less than 2. Ideally, you should stay around 6 or 7. That is the smallest discretization you should try to use. Otherwise, you will be arbitrarily changing the stiffness behavior of your model and you will start getting unusual result. And this is assuming that the Poisson's ratio is 0.25, say something akin close to concrete. And if you take a look at this is in the case of a what do you call it, a restrained cantilever. But if you have a free cantilever, then you notice that even you can discretize it even smaller, even if you take a ratio of 1:3, 2, also is reasonably flexural behavior is maintained. Even at the smallest L by D ratio, the flexural deformation contributes to 70%, whereas it contributes to only 30% in the case of a restrained cantilever. And your normal one will be somewhere in between them. Normal one, it will be somewhere in between them. Therefore, discretization of any flexural member is also important for you to study and understand that before you use it blindly. Okay, that's for the day. We'll continue with further modeling exercises in the next class. Now I am open to any questions you may have. Okay, if you don't have any questions, we'll meet again next Friday, same time, 4 o'clock. Okay. Right. Bye. Good night to everybody.